was exposed to the deadly dose of radiation. Again, isotope visualization with ionizing radiation. Boom, 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 boom. Space is silent, but it's not empty. Radiation pulses, particles fly, machines listen, but sometimes the quietest signals are the most profound. In today's episode, we're going to talk about the different types of radiation that help us detect the unseen, the different dangers that exist with that, and kind of talk about radiation, sound, different subtle waves, and things like that. I want to talk about things such as the Demon Core. This little device here, which for those listening you won't see, but you might be able to hear the little clicks that come along with it. This is a radiation detection device. And I will leave that going on in the background there. But we're going to talk about all these things, radiation, the different types of radiation, what ionizing radiation is versus non-ionizing radiation, which really I think gets a lot of people confused, especially with the day and age of people scared of 5G and things like that. So we're going to talk about all these things. And then what are we going to talk about? We're going to talk about sonar, why it doesn't work in space, ultrasound and how that works, specifically about ultrasonic leak detection on the International Space Station. And we're going to talk about different types of wave-based detectors in space. And again, what the difference is between radiation in space versus the radiation here on Earth and how it affects us, how we're protected here and how we're not protected in space. And really the unknowns of things like galactic cosmic rays or GCRs. And really what all this means to us. So I hope you guys enjoy this episode of the RedMars podcast with myself, Astro Jake, and we'll see what y'all think of this. So let's get started. All right, so before we talk about all these different things, we need to understand what radiation is. And we're going to start with ionizing radiation because this is really the most scariest of them all. So ionizing radiation is kind of classified in different parts. So we have alpha radiation. These are typically helium nuclei, so 2 protons, 2 neutrons. And they are very low, typically stopped by paper or skin. So it's not really, it's a low risk. You don't have to worry too much about these alpha radiation. They're harmful if you're ingested or inhaled, and they typically come from radioactive decay like uranium, radon, things like that. And a fun fact that I learned going into this, and by no means am I an expert, by the way, in radiation or anything like that, but by talking about this, I am learning as you are learning. But I learned that in Iran, they actually have very rich, radium or uranium soils? I'm definitely getting that wrong, but they have these types of radioactive material that is in the soil due to the springs coming from underneath the surface of the earth and kind of bring these hot waters and that into the soil, and it also brings with it this radioactive material that increases the amount of radiation they're exposed to, which is similar to the radiation exposure that you would get living on the International Space Station. So that's quite interesting. So anyways, continuing along here, we have beta radiation. So there are high energy electrons or positrons. They have a moderate penetration capability, so they're stopped by aluminum or plastic. So those little aluminum hats they wear that actually, does a good job of stopping these beta particles. I wish I had a smoke chamber here, and we could put some small, not really harmful radioactive material in there, and you could see the alpha and beta particles kind of shooting off. If you've never seen a smoke chamber, maybe I'll find a video here somewhere on the video, and we can take a look at that. But this typically comes from radioactive isotopes like carbon-14, strontium-90, things like that. And external exposure to the skin and internal exposure are both ways that this is dangerous to humans. All right, gamma radiation, so electromagnetic waves or photons. So they have a high penetration. It requires lead or several inches of concrete to protect, and this can damage internal organs and DNA. Nuclear reactions, radioactive decay are also sources of these gamma radiation particles. And when we say damaging DNA, what this really means, and again, not a medical expert, but I'll just kind of explain very high level what this is and why it's dangerous. So you have your DNA, and when a gamma particle comes in, it comes running in there real fast and throws some of those I guess, parts of your DNA apart. I won't go too technical here. So it's just damages a piece of your DNA and creates a mutation. That mutation now is part of that DNA strand in that cell, and when that cell now duplicates and continues to duplicate and duplicate, so does that mutation. And this mutation could be harmless or it could be cancerous, and you could end up with a cancerous mutation that duplicates and becomes growth in the human body. So very high level, and again, not a medical expert, so no idea what actually goes on, but high level, that is how I understand it, that the radiation damages a DNA strand, creates a mutation or multiple mutations or whatnot, depending on the size of the radiation particle that hits the DNA, and that could be harmless or could be harmful, and when that cell duplicates, so does that mutation. All right, moving on. We have X-rays, so electromagnetic waves. Again, that's what spectrum is part of. So penetration, similar to gamma, but usually lower energy. That lower energy then equates to less damage. It's usually used in medical imaging and security cameras, and the source of this is accelerated electrons hitting metal targets. And this is why we can be exposed to X-rays for medical purposes and pose very little risk, and it's because of the lower energy that is equated to that. So next we have neutron radiation. The particles are called free neutrons. So penetration is very high, requires water, concrete, or borated materials. So the source of this is typically nuclear reactors, some radioactive decay, and then we have those cosmic rays, which are very dangerous. And again, we don't really know where they come from. Some people say it originates from black holes, other people say from the beginning of the universe, and other people believe it's from dying stars when they implode and then expel all these types of galactic cosmic rays, those GCRs. All right, so that is your ionizing radiation. Then we go into non-ionizing. So this is typically less harmful in terms of comparison to the ionizing. Can still be harmful, obviously, but so let's start with ultraviolet. So UVs. So this is when you go out and get a tan or get a sunburn or something along those lines. Even a tan is your body's response to interacting with the UV rays, and it's not a positive response. If you see a tan, that is actually already damage to your DNA and your skin. So the types, there's UVA, UVB, and UVC, and the danger, again, causes skin burns and DNA damage, especially UVB and UVC. The sources of this are the sun and UV lamps, so that's like your tanning beds and stuff like that. So those that believe that getting a tan is your body's response to protecting you from the sun due to the melanin, incorrect. That is actually, and again, not a medical expert, so again, take it with a grain of salt, but typically, or not typically, what this is that DNA damage, and your body, if you see a tan, has already been responding to these UVBs, UVC rays, and you got to be careful on exposure. So wear that sunscreen. Obviously, there's bad sunscreens out there too, so wear sunscreens that are good for you, or at least have shown through studies to be better for you. Obviously, it's a balance of the two, so sunscreen's better than the UVB and UVCs because typically you don't get the same DNA damage. Anyways, again, not a medical expert. So visible light. So electromagnetic radiation visible to the human eyes. There's no real danger here. It's just illumination, signaling, and photosynthesis. Good old photosynthesis. Next we have infrared. So this is heat radiation. So thermal imaging, heaters, and remote controls. Think of, remote control for your TV, although most of these are now radio, which we'll get into as that is another version of non-ionizing radiation. Then we have microwave. So this is what you use to cook, as well as your Wi-Fi is also in the microwave range. So it's used for, as I mentioned, cooking and communications. And how it interacts is it causes molecules like water to vibrate. And this is actually how the cooking works in your microwave, and why it's dangerous to humans if you were to be exposed to those higher levels of microwaves, because what it does is vibrates those water molecules, creates friction, which creates heat, and then cooks you. So that is how your food gets cooked. That's why if you put something in the microwave that doesn't have water molecules in it, it doesn't get hot. So that's why, a paper cup in the microwave, if there was no water in that paper cup, is just an empty paper cup, it's not going to heat up due to the microwaves. And yeah, cool thing. Anyways, radio waves, AM, FM radio, cell phones, TVs. So this is the longest wavelength and the lowest energy. And because it's that lowest energy, again, it's not really dangerous to humans, and that is why 5G falls into this radio waves as well for your cell phone, and is not dangerous, regardless of all the conspiracies that are out there saying that radio waves are dangerous. It's low energy, it's not causing any real dangerous vibration of water molecules that are cooking you. So you're not walking around getting cooked. Otherwise, we'd all be cooked by now, and that would be the end. All right, some other types or special types of radiation that exist out there. We have cosmic rays, which are high energy particles, mostly protons from space. And then we have Cherenkov radiation. Cherenkov radiation, blue glow seen in nuclear reactors. And this is going to be similar to when we talk about the demon core, which is interesting story, absolutely terrifying and sad, all in the same, but we'll get to that. And then we have just background radiation. This is natural radiation from Earth, the atmosphere, and the cosmos. So the Earth obviously gives off radiation. In the electromagnetic spectrum, we have the Van Allen belts, which gives us some protection from those GCRs, those galactic cosmic rays as well. And really, we're surrounded by it. There's no escaping radiation. It is there to stay, and it will always be there. It's just how do we cope with it, understanding the different types of radiation that exists, and which ones are harmful and which ones are not, and just what we can do to protect ourselves in the different environments and radiation environments that we're exposed to, which brings us to this guy. And so by no means am I sponsored by these guys. I wish I was, because I would like to get the higher models of the radio code. But yeah, so let's talk about this guy. So on my screen here, I have the website, which is www.radiacode.com. That's RADIACODE.com. So for those listening, definitely go check it out. It's a super cool device that I came across. And it comes with an iPhone app, and as you can see on the display here, it shows it's got the spectrometer. It gives you an overlay of Google Maps, kind of like a heat map showing where you've traveled, what it looks like on there, different levels of radiation that you were exposed to on your travels. And I did a fun video like this where I traveled from my house across the state of Florida and stopped at a McDonald's, got some food, and then kept going along. And the funniest part was the highest radiation that was detected on this detector was actually in the parking lot of the McDonald's, and this could be due to many different factors, including newly paved roads and stuff like that. So by no means am I saying that McDonald's had radioactive material in their food or anything like that that was harmful, but it was just a funny video I put together, and interesting to see that that's where the spike was. Now again, that spike was still well below any harmful level that you would experience, and there's actually a chart, I believe, somewhere on government site here in the US that goes through what the exposure levels, just kind of background radiation living in the US you were exposed to versus going into the space station and all that. It gives different levels and breakdowns of what you're exposed to and what is considered safe, and the CVOLT ratings for this of like exposure and that's based on current knowledge of radiation exposure and the risk of cancers associated with that exposure rating. So interesting stuff. For those that are interested, definitely encourage you to go check it out. But back to this device. So this is the world's first series of pocket-sized radiation detectors and spectrometers engineered for all natural science enthusiasts. So they are a great little device with a very powerful app for your phone. You can use it to show accumulation, track your kind of heat maps as you go. So yeah, radiation tracks with Google Maps, energy and temperature compensated dose rate and spectrum, food testing mode for contamination, mobile and PC applications with extra features. It's got all kinds of stuff. These are made in Europe. They come with a 2-year warranty, and there are some new models out here. So I started off with just the basic one here. This is the radio code 102. Kind of goes into some specs here, the cost of it. So yeah, $229. You can get them on Amazon. You can buy them from the website. And you have the radio code 103, which I believe is just a bit more sensitive, bit more advanced features, and I think it does alpha particles better, or gamma maybe. I don't recall. I'd have to look at the specs on this one. The radio code 110 is the top sensitivity, so it's even more sensitive than the other ones. There you go, 77 CPS, so that's 1 microsolvol per hour for CS 137. And then there's the radio code 103G, which has the top spectrometry. So I'd love to get a combination of the two, like one in each, or maybe this one with the radio code 110 would do it. But The 103G, I think, is where I will go next. They start shipping August 31st, 2025. They are pretty steep at $600, but if this is a field that you are interested in, or you're into these earth sciences and space sciences and just radiation in general, whether it's from, a prepping standpoint or just science standpoint, interest, whatever, these are all great devices. So by no means do you have to go with the 103G or 103. You could start with the 102 like I did, and it really gets you into this space and learning about radiation and what exposures look like, reading through spectrometry graphs, and all that. And it's really neat. So here's a 1-minute video, and hopefully the audio shares through. For those listening, this is a video that explores kind of the features and that of the radiocode detector here. So let's play this. And I'll just pause it here just in case none of this is audio is coming through. Pretty much just showing the features of the device, being able to hold it up to different things like stones. I've seen them use these for old houseware items like pots and pans with the different types of lead and paints and stuff like that in them. And you can see the different heat maps here. So here's they're showing them as they walk through cities. Funny, they went to Ottawa. You can see different isotope information based on the spectrometer graphs. Skipping ahead here. Alright, so we'll just leave it at that. But yeah, super awesome device. Definitely for anybody interested, highly recommended. Yeah, they're just a lot of fun. Yeah, here we go. You got old alarm clocks, uranium in some of these older pottery or, I don't know, cups and stuff like that. Nuclear isotope visualization. Yeah, so this is gamma spectrometry, once at the domain of bulky lab rigs, costing tens of thousands of dollars, now fits in your pocket. Paired with a free smartphone app, the 67-gram radio code lets you visualize the energy lines of incoming gamma rays and explore natural sources like potassium-40, thorium-232, cesium-137, radium-226, and more. It's super fascinating. Yeah, again, I can't talk more great about this device and the company itself and really what they've done here to make this accessible to everybody. So excuse me, sorry. This is definitely one of the better devices out there. There are some cheaper options that exist, but I can't really speak to the quality of those devices. I've been using this one for probably about a year now, and yeah, it works great. The battery is super long, charges with a USB-C. It's got different LED indicators on the top. I don't know if you can see that in the camera there. I can push the button here, unlock it so that you can see. Let me see. Yeah, it's kind of hard to see, but on the device there, it'll give you a small, can I do it so it doesn't glare there? Kind of gives you a little graph printout, so you can see if you don't have your phone on you or anything like that. You can go through different menus and stuff like that, and there's some really cool features. Let's see. Yeah. Anyways, it's cool. I enjoy it. It's a lot of fun. I'll turn that off now so you don't keep hearing the beeping in the background. But that is the radiocode device here. Yeah, once maybe I can get them to send me one of the newer ones here, and we can see how this guy works, do a review on it, and take it exploring with us as we go travel around. So we'll see. But enough about the radiocode. Let's dive into an interesting story on the Demon Core, which is this guy you see on my screen here. So we're going to talk about this incident, 1945, and how it took someone's life extremely quickly, more so in a flash. They didn't die immediately, but I think it was within a week or so later, died of different types of cancers and stuff like that due to this experiment. So we'll get into that in a second. All right, so the demon core. So the demon core was a subcritical mass of plutonium intended for a third nuclear bomb during World War II. In 1945 and again in 1946, two separate incidences occurred during criticality experiments, resulting in lethal radiation exposure to the physicists involved. And I think it also happened to one of the security guards that were in a room close by, and others in there. Obviously, the radiation exposure varied based on how close you were and what stood between you and the so-called demon core that you can see on my screen here. But actually, I guess I'll talk about what the experiment really was. So this demon core has these tungsten carbide blocks around them, and the idea was you take this subcritical mass of plutonium and reflect particles back at itself. And you can do this to a certain point that it would slowly get closer and closer to criticality. Criticality is when you get that boom and particles start reacting with each other to an extent that you get that nuclear reaction. And really, that's kind of what but the idea of this experiment was reflecting the particles back at the plutonium such that it would get closer and closer to reaching criticality without actually hitting that criticality event. And so they would place these blocks around this sphere of plutonium, reflecting those different particles back at the plutonium, and see how close you can get. And so during this experiment, who was it? The first person? No, that's the second. Who was the first? I'm not sure. So the second person was Louis Slotin. He was the second victim. Yeah. Okay. So, anyways, the first victim. What happened was they dropped the brick, and the plutonium very quickly reached criticality. Huge blue flash happened, and he quickly went and hit the brick with his hand to remove it, to stop the plutonium from creating that criticality event. And anyways, he did this, and what happened was the burst of neutron and gamma radiation more or less hit all types of mutations, or created all types of mutations in his DNA that then duplicated, as we were talking about, which caused him to die of radiation sickness shortly thereafter. And more or less he got like cooked from the inside out, which is pretty terrible. But yeah, let's kind of walk through this. So the accidents happened because of small slips in equipment positioning that caused the core to go briefly supercritical. And what that means is it emits that fatal burst of neutron and gamma radiation. So Louis Slotin, he was the second victim, used a screwdriver to manually separate two beryllium hemispheres, acting as reflectors. The screwdriver slipped, and in an instant the core went critical. He slammed the hemispheres apart, but was exposed to the deadly dose of radiation. Again, we're talking like very quickly, like a second or so of this critical event, and bam, that's a lethal dose. So he died 9 days later. Others in the room were exposed as well, some dying years later of complications. This is when you get those mutations that then duplicate in the body, and you get different types of cancers and whatnot that usually lead to different types of organ failures and, unfortunately, loss of life. So the event of why we now use remote handling tools and automated systems for dangerous radiation experiments as a reminder for the unseen lethality of certain radiation types. So that's the reason we treat radiation with respect. Yeah, in the 1940s, a sphere of plutonium only 3.5 inches wide came to be known by a haunting name, the Demon Core. That's what's in this picture here. It didn't explode. It didn't create a mushroom cloud, but in a flash, yes, it killed. Not with a sound or heat, but with a silent, invisible wave of energy. Radiation detection became more than a curiosity at this point. It became a matter of life and death. And now, this day, we have one of these that, again, can really give you insight to this unseen danger that exists. So, again, not sponsored, but go get one. All right, so the demon core, the invisible radiation with deadly consequences, and then we go whole other side of the spectrum, quite literally, the ultrasound, invisible waves that let us see life and leaks and all kinds of stuff. So that leads us to our talk about ultrasonic detectors used on the International Space Station. So they use ultrasonic detectors to safely identify dangerous and costly leaks. And the way this works is different vacuum leaks and whatnot on the space station create a turbulence in the air that is in the confined atmosphere of the space station where the astronauts live. And that disturbance or disturbed air emits an ultrasonic sound. Obviously, we can't hear it, but with these ultrasonic detectors, they can use these to pinpoint the leaks and repair them as needed so that they don't grow into larger leaks and ultimately put the astronauts' lives at danger. So we'll read through a little bit of this here for those listening. For those that are watching, you can see where this comes off from. So this is from NASA's website, but yeah, let's just dive into the first part of this. So in 1990, NASA grounded its space shuttle fleet. The reason leaks detected in the hydrogen fuel systems of the space shuttles Atlantis and Columbia. Unless the source of the leaks could be identified and fixed, the shuttles would not be safe to fly. To help locate the existing leaks and check for others, Kennedy Space Center engineers used portable ultrasonic detectors to scan the fuel system. As a gas or liquid escapes from a leak, the resulting turbulent creates ultrasonic noise, explains Gary Moore, president of Elmsford, New York-based UE Systems, Inc., a longtime leader in ultrasonic detector technologies. In lay terms, the leak is like a dog whistle, and the detector is like the dog's ear. Yes. So because the ultrasound emissions from a leak are highly localized, they can be used not only to identify the presence of a leak, but also help pinpoint the leak's location. So the NASA engineers employed UV detectors to examine the shuttle's fuel tanks and solid rocket boosters, but encountered difficulty with devices' limited range. Certain areas of the shuttle proved difficult or unsafe to scan up close. To remedy the problem, engineers created long-range attachment for the detectors, similar to a zoom lens on a camera. Moore says if you are on the ground and the leak is 50 feet away, the detector will now give you the same impression as if you were only 25 feet away. The enhancement also had the effect of reducing background noise, allowing for a clearer, more precise detection of a leak's location. This technology then transferred and is also used on the International Space Station, as we mentioned. And so the benefits of this is a long-range module has since proven to be a valuable addition to the UE's commercial offerings. And they say, we have maintained the original design since the beginning of the license. It works really well for our customers, and that's what we care about. So UE system detectors play a key role in managing safety, cost, efficiency, and environmental impacts across a broad range of industries. In addition to leak detection, the major applications for technology include ball bearing and mechanical inspection, electrical inspections, and valve testing. Detecting leaks in factory compressed air systems is perhaps the technology's most valuable use, says Moore. Yeah, we won't read all the way through this. If you want to read more about kind of this technology, though, and how it works, definitely go check it out, spinoff.nasa.gov, and spinoff 2012 is kind of what you're looking for there. So that'll give you the information you need on the ultrasonic detectors and kind of a little bit more into how they work and how they keep astronauts safe. So it's pretty cool that technology is developed for, space systems and whatnot can be used elsewhere here on Earth. And there's just a lot of benefit to kind of throwing all this money at these different space missions that may seem to others as a waste, but really the technologies that come from it really help us here on Earth as well. Everything from ultrasounds that are used for detecting babies, and the same technology is used for detecting leaks in space. Not saying that the space came before the baby. I actually don't know the story on that. Actually, that'd be an interesting one to look into. But just really that the technologies here and the money that goes into research and whatnot is not just for space itself. It usually derives other technologies that benefit humans here on Earth as well. So that's kind of where I'm going with that. All right, what shall we talk about next? What about wave-based detectors? So that's things like LiDAR, radar, radio telescopes. And now, as we get into the world of AI, we have AI analyzed RF scans like SETI, And then again, being able to see the unseen, which is a recurring theme for space exploration. So we might not be able to see it, but radio waves can give us that image or picture into deep space of what the human eye cannot see, because again, we are limited to just the visual spectrum. So radio waves and radio telescopes are what we're going to talk about next. So what are radio telescopes? So the National Radio Astronomy Observatory, NRAO, tells us that just as optical telescopes collect visible light, they bring it into focus, amplify it, and make it available for analysis by various instruments, so do radio telescopes. They collect weak radio light waves, bring it to focus, amplify it, and make it available for analysis. We use radio telescopes to study natural occurring radio light from stars, galaxies, black holes, and other astronomical objects. We can also use them to transmit and reflect radio light off a planet body in our solar system. These specifically designed telescopes observe the longest wavelengths of light, ranging from 1 millimeter to over 10 meters long. For comparison, visible light waves are only a few hundred nanometers long, and a nanometer is only 1/10,000th the thickness of a piece of paper. Your standard paper, of course. So in fact, we don't usually refer to radio light by its wavelength, but by its frequency. So, natural occurring radio waves are extremely weak by the time they reach us from space. So a cell phone signal is a billion times more powerful than a cosmic wave our telescopes detect. And we recently just talked about how they are very low energy, those cell phone signals, and those radio waves that are used for that, and that's why they're not dangerous to humans. So these other radio waves we're talking about now that radio telescopes pick up are even less, what we just mentioned, billion times more powerful, so billion times less powerful than what our phones are using. So let's talk about how this is possible. What are the parts of a radio telescope? So radio telescopes are built in all shapes and sizes based on the kind of radio waves that they pick up. Yes, and so similar to antennas, if you've ever looked at building an antenna or anything like that, I did it for one of my wireless communications courses during my undergrad at Carleton University up in Ottawa, Ontario, Canada. And you learn that there are certain optimized sizes of antennas that correlate to the wavelength of the actual radio wave itself, and so you'll use things as a fraction of that, typically because if you have say, how long was this thing? 10 meters long. The perfect antenna, maybe not perfect antenna, but an ideal antenna for that, if you could build it, would be a 10-meter long antenna. Now, you want to do a fraction of that because it's a lot more practical, so you might do, a quarter wavelength or an eighth wavelength, and that still will be adequate. Now, the bigger you can get to match the wavelength, the better it'll be for that radio telescope or that receiver, because it's able to be a bit more sensitive and really hit or capture that entire wavelength of radio waves. So I'm sure they'll talk about the size here. But so radio telescopes are built in all shapes and sizes based on the kind of radio waves they pick up. However, every radio telescope has an antenna on a mount and at least one piece of receiver equipment to detect the signals. Because radio waves are so long and cosmic radio sources are extremely weak, radio telescopes are the largest telescopes in the world. Right, so that's kind of what we were just talking about. And the most sensitive radio receivers are used inside them. Unfortunately, these huge antennas also pick up radio interference from modern electronics. A great effort is taken to protect radio telescopes from radio frequency interference. So this is when it dives into the antenna. There's a little diagram here. Let me see if I can zoom in here a bit. Oh, that went real big. That might be too. Let me zoom out here. I didn't realize I was going to zoom in my entire screen. Let's try this. There we go. All right. So for those watching, you'll see radio telescope. You see incoming waves bounce off this concave dish, and they hit the reflector in the center, which then goes to the sensor, which is the receiver that amplifies and detects the radio signals. So radio waves reflect off the dish and focus at the tip. And it's very similar to how a reflective telescope works as well, except for this is just for radio waves. So that's exactly what it is, a radio telescope. So obviously it would work in a similar way. And we're also, the way light waves bounce, this is the same way. So it's just non-visible. to us at least. So yeah, so that's how the antenna in that works. Very cool. Let me zoom this back out to what it's supposed to be at. All right. So let's see. The dish surface, this is definitely important. So if the lengths of radio waves we are studying are very small, such as millimeter waves collected by ALMA, A-L-M-A, then the perfection of the telescope's dish surface is critical. Any warp, bump, or ding in the parabolic structure, that's that concave, that we were just showing, it'll scatter these tiny waves away from focus, and we'll lose that information. So think of like frequencies in the gigahertz. Those are much smaller. That's why you'll see antennas that are sometimes on a printed circuit board, that tiny, in different geometries and whatnot. You can optimize for receiving patterns and all that. But any of these, if you think you have a very small wavelength, say even in the nanometer range or something like that, or centimeters even, and you have a crack in a dish or a rough surface, think of like a ripple in a water, and you stick your finger in the path of that ripple now gets disturbed and you get noise in there, and that signal has now been interrupted. So the same thing happens here. So you really want the surface of those dishes or the concave material to reflect as smoothly as possible. So that's why they say that any bump, ding, anything like that will scatter these tiny waves away from focus, and we'll lose some of the information. That's why things like what's that telescope there that they just put up with the gold dishes, whatever, it's they're extremely smooth, and any imperfection in that, it's a radio telescope, well, the James Webb, yes, it will interfere with the images that it's capturing. Now it's got many of these, so it can use that and put together images and help with that as redundancy, but things you need to worry about. So if the size of a radio wavelength being observed is very long, such as the centimeter waves picked by the VLA and VLBA, these are different systems as well, then the perfection of the dish shapes not as critical to keep excellent observations of the radio sky. Those dishes are made of rigid and tough and withstand the rigors of moving and working in various conditions. And then we have telescope mounts. Again, all these things, because we're dealing with wavelengths, you have to be very careful how they're built, how they're moved. Everything, piece of electronics, any type of vibration affects that, because really how this works is it's going to vibrate at the frequency of the radio waves that it's receiving. That's why you want to stay, the quarter and eighth wavelength, or the wavelength itself, and any vibrations disturbs us. Again, back to our ripple that we were talking about. You have a ripple, you put your finger in the way, you've now disturbed it. Well, now if you vibrate the water over here, some of these waves might actually cancel each other out, and you end up with dead zones, and all of this just interferes with that image that you're trying to receive. And then we get into data processing, and I won't read through this one, but pretty much there's different ways of processing radio waves that allow you to retrieve information, do some correcting as well. There's now AI that can be used to analyze and put things together based on patterns and whatnot in the images that it's receiving and signals that it receives, and it's very cool. But we use arrays. Here's an image for those looking that you have this really cool kind of delta array here, almost looks like a Mercedes symbol. So this is flying southward over the very large array in central New Mexico. Shows the flatness of the plains of San Agustin, where the array is sited at over 7,000 feet elevation. This ancient lake bed provides the space needed to lay 40 miles of double track rails required to extend the VLA's Y shape to give us the highest resolution capable. And so why would we use an array? So the ability of a radio telescope to distinguish fine detail in the sky, called angular resolution, depends on the wavelength of observation divided by the size of the antenna. Again, this is where we talk about our wavelengths and all that we were just talking about. So in other words, to get the finer detailed views of the sky, the result of that simple equation needs to be a very small number. So radio telescopes observe long wavelengths. So even when we divide our shortest radio wavelengths by our largest antennas, we still only have an angular resolution similar to that of the unaided eye observing the sky. So to have their resolution compared to optical telescopes, a radio telescope's antenna size needs to be much, much larger. Right, so the largest moving radio dish is the Green Bank telescope, 100 meters across and fully steerable. That is ridiculous. That's huge. So the world's most gargantuan radio dish, the 1,000-foot bowl in Arecibo, Puerto Rico, can move, but it it can point on the sky moving its receivers, but it can point on, oh, weird. Okay. I don't know why that sounded weird to me. So the dish is supported inside a large sinkhole in the island's karst terrain. That's super cool. No picture here, but definitely go take a look at that. It's really neat. So the very long baseline interferometry, the VLBI. So here's another picture of that one there. And yeah, radio telescopes are super interesting, super cool. A whole world of science just on those alone. Again, like I mentioned, I did some work in my undergrad on antennas, and I did mine for ADS-B so I could listen to the aircraft flying overhead, and wanted to build an antenna that was optimized for that frequency. And it worked really well. It was super neat. You can use different devices to measure them. The VNFs or spectrum analyzers can help you better understand the quality of that antenna and the frequency that it's tuned for. The VNF uses, or you can use a VNF for checking the tune of that of the antenna, and then the spectrum analyzer, or you can use these to get the pattern as well of the antenna itself. But yeah, that's radio telescopes. What else do we want to talk about? I think that was more or less all the information I want to go in here, and I don't want to talk too much about everything here, but yeah, so we talked about radiation, sonar, ultrasound, tools we use to explore the vast unknowns of space. Sometimes the most meaning discoveries happen a little closer to home. So I've got an image here for those that are watching. I'm going to put that up on the screen somewhere here. And yeah, that is my reveal of today's episode. So very excited about this, and hope you are too. I don't normally share much personal stuff on my podcast, but for friends and family listening, this one's for you guys. Take a look at this image. If you're listening, definitely watch the video if you want to see what I'm talking about. This is in relation to the ultrasound that we talked about. Ultrasound technology is not only used just on the space station for leak detection, but yes, the beginning of life. So very excited to share that with everyone. And I'm just going to leave that there. But yeah, thank you everyone for today's episode. I hope you enjoyed the talk about radiation, and I hope you have a better understanding of the different types of radiation that exists out there in space on Earth and whatnot, and what ionizing is and what's non-ionizing, so you can better explain to friends and family and folks when they say, oh, that 5G is killing us all. You can be a bit more informed about what's actually going on. And yeah, so with that, take care. I hope you all have a great day, and I will catch you all on the next video. See you all soon.